On September 22, 1943, a column of battered tanks rolled back through the gates of Bovington camp in Dorset. They had been driven nearly 3,000 miles across England over the past 7 weeks, pushed to their mechanical limits on every road surface the British Isles could offer. Paved highways and cobblestone streets, muddy farm tracks and forest paths, steep hills and river crossings. The exercise was classified most secret. Its findings would reshape British armoured doctrine. Major Clifford, the officer commanding the trial, had watched these tanks struggle and succeed across 2,000 miles of English countryside. Now, as he prepared his report for Major General A.C. Richardson, Director of the Royal Armoured Corps, he chose his words with the precision of a man who understood what was at stake. Of the American Shermans, he wrote that there was little he could say. This type of tank seemed almost without reproach. Personally, he would be delighted to take a Sherman squadron to war. They were utterly reliable. Of the British Cromwells, his assessment was more guarded. This tank had the makings of a wonderful fighting machine, but he did not consider it to be out of the experimental stage yet. The numbers told the story that words alone could not. The Sherman force had covered 13,986 miles, with just 199 defects, requiring 420 hours of fitter attention. That worked out to 0.03 maintenance hours per mile driven. The Cromwells managed 11,582 miles but accumulated 367 defects, requiring 814 hours of repair, 0.07 hours per mile, more than double the Sherman's requirement. This was Exercise Dracula, and its findings would echo through the rest of the war. The M4 Sherman was America's answer to the challenge of mechanized warfare. Designated medium tank M4 by the United States Army Ordnance Department, it was named after General William Tecumseh, Sherman of Civil War fame by the British, who had a tradition of naming American tanks after American generals. First produced in February 1942, it would become the backbone of Allied armoured forces on every front, from the western desert to the hedgerows of Normandy to the volcanic islands of the Pacific. The tank weighed approximately 30 to 33 tons depending on variant and carried a crew of 5. A commander, gunner and loader occupied the turret, while the driver and assistant driver sat in the forward hull. Its 75mm main gun could engage most enemy armour at combat ranges. A coaxial 30 caliber machine gun mounted beside the main gun provided infantry support, while a second 30 caliber in a ball mount gave the bow gunner defensive capability. Many Shermans also carried a 50 caliber heavy machine gun on a ring mount above the commander's hatch. The Sherman stood nearly 9 feet tall, a silhouette that made it an easy target, but also gave its crew excellent visibility over the battlefield. This height was a deliberate design choice driven by the need to accommodate the radial aircraft engine that powered early variants. Critics called it a barn on tracks. Defenders noted that high ground clearance allowed the Sherman to traverse terrain that bogged down lower vehicles. What made the Sherman truly remarkable was not its armour or its firepower. Both were adequate but not exceptional. German Tigers and Panthers outclassed it in both categories. What made it remarkable was that it kept running when other tanks broke down. The Sherman proved this on October 23, 1942, when 252 M4 tanks supported the British 8th Army at the Second Battle of El Alamein. It was the Sherman's combat debut, and it came a full 20 months before the Cromwell would fire its first shot in anger. British tankers who had struggled with unreliable crusaders suddenly found themselves in machines that started every morning and ran all day without complaint. The Sherman was not perfect. Its armour would not stop German 88mm rounds. Its 75mm gun struggled against the frontal armour of late-model Panzer IVs, but it was there. It worked. It fought. The Tank Museum at Bovington notes that the Sherman gave British forces a flexibility they had never before possessed. When the British needed a tank mounting the powerful 17-pounder anti-tank gun, they simply fitted it to a Sherman, creating the Firefly. No British chassis could then accommodate the weapon. The Sherman's larger turret ring made the modification possible. The Cromwell represented Britain's attempt to produce a fast, powerful cruiser tank that could match German armour in mobility, if not in protection. Officially designated the A-27M Cruiser Tank Mark 8, It traced its lineage through a complicated development history that reflected the challenges of British tank procurement during the early war years. The tank entered production in January 1943 and first saw combat on June 7, 1944, the day after the D-Day landings. The Cromwell weighed roughly 28 tons combat-loaded and carried the same 75mm gun as the Sherman. Its crew of 5 operated in somewhat more cramped conditions than their American counterparts, particularly in the turret, where the ring diameter measured just 60 inches compared to the Sherman's 69 inches. This cramped turret made crew escape more difficult and slowed the loader's rate of fire. The Cromwell's greatest asset was its engine, the Rolls-Royce Meteor. Derived from the legendary Merlin that powered Spitfires and Lancasters, the Meteor produced approximately 600 horsepower at maximum operating speed, though at the governed speed of 2,250 revolutions per minute used in service, it delivered roughly 540 horsepower. This gave the Cromwell a governed top speed of 32 miles per hour. Ungoverned, test vehicles reportedly reached over 40 miles per hour, making it the fastest British tank of the war. Both tanks emerged from nations fighting for survival against Nazi Germany. Britain had stood alone against Hitler from June 1940 until the German invasion of the Soviet Union in June 1941. America had watched from across the Atlantic before Pearl Harbor brought it into the war in December 1941. Now both nations poured their industrial might into producing the weapons that would defeat fascism. But the industrial cultures that produced their tanks could not have been more different. The Sherman was born in Detroit, the heart of American automotive manufacturing. Since Henry Ford introduced the moving assembly line at Highland Park in 1913, American industry had led the world in mass production techniques. Ford, General Motors, and Chrysler had spent 3 decades perfecting the art of turning raw materials into identical automobiles. Interchangeable parts meant a carburetor from one factory fit an engine from another. Assembly line efficiency meant workers specialized in single tasks performed thousands of times. Quality control systems ensured that every vehicle leaving the factory met precise specifications. When America entered the war, these companies simply applied the same methods to tanks. The transition was not without challenges. A tank was not an automobile. It weighed 20 times as much. Its armor had to stop artillery shells. Its engine had to drive it across terrain that would destroy any car. But the fundamental principles translated: break production into specialized steps, make every part interchangeable, test ruthlessly, and reject anything substandard. The Chrysler Defense Arsenal in Warren, Michigan, exemplified this approach. This purpose-built facility was designed by architect Albert Kahn, who had designed the Ford Rouge plant and dozens of other industrial landmarks. The government funded construction with $21 million, and Chrysler operated it under contract. By December 1942, barely a year after Pearl Harbor, the arsenal's workers were producing over 900 Sherman tanks in a single month. This astonishing rate of production would have seemed impossible to European manufacturers. British factories struggled to produce 50 tanks monthly. German factories, despite their reputation for engineering excellence, never matched American output. Across 10 factories in the United States plus the Montreal Locomotive Works in Canada, approximately 49,000 Shermans rolled off production lines between February 1942 and July 1945. The factories included familiar automotive names like Ford, General Motors, and Chrysler, alongside industrial concerns like Baldwin Locomotive Works, American Locomotive Company, Federal Machine and Welder, Lima Locomotive Works, Pacific Car and Foundry, Prest Steel Car Company, and Pullman Standard Manufacturing. The standardization was extraordinary. A turret manufactured at the Prest Steel plant in Chicago could bolt directly onto a hull from the Fisher Tank Arsenal in Michigan without modification. An engine from Ford's Highland Park facility would fit perfectly into a tank built by American Locomotive in New York. Transmission assemblies, suspension components, electrical systems, all were truly interchangeable across manufacturers and production runs. This interchangeability enabled a revolutionary approach to battlefield repair. The American Army developed a multi-echelon maintenance system that could return damaged tanks to service with remarkable speed. A Sherman destroyed on a Normandy hedgerow could donate its surviving turret to replace one knocked out by a Panzerfaust. Its engine might go into a tank whose power plant had burned out. 3 destroyed tanks might yield 1 working vehicle, plus a stockpile of spare parts. Field repairs that would immobilize British or German tanks for days could be completed on American tanks in hours. An engine swap, one of the most complex field repairs possible, could be accomplished in little more than 4 hours, according to documented wartime assessments. Every component was designed for accessibility. Updated parts maintained backward compatibility throughout the entire production run. Britain's tank industry operated on fundamentally different principles. The engineering tradition that had produced the Rolls-Royce Merlin aircraft engine, arguably the finest piston aircraft engine of the war, emphasized craftsmanship, performance, and individual excellence. British engineers pursued technical perfection. They pushed boundaries. They created machines that extracted every possible ounce of performance from their designs. These were admirable qualities in peacetime. In the crucible of total war, they became liabilities. A Soviet inspection team that visited Nuffield organization factories in Birmingham on March 1, 1943, found a telling detail. Engine assembly involved manual fitting with chisel and file. Workers hand-adjusted components to achieve proper tolerances. This craft-based approach produced excellent individual engines, machines that might outperform their American counterparts on the test stand. But it could not scale to meet wartime demands. Nuffield, one of Britain's largest industrial concerns, produced just 2 Crusader tanks per day. That worked out to roughly 52 per month under ideal conditions. A single American factory could exceed that in a week. Cromwell production involved 10 or more manufacturers, including Birmingham Railway Carriage and Wagon Company, Metro Camel, English Electric, Leyland, and Nuffield itself. Soviet intelligence identified 22 assembly plants across these firms. Each had varying capabilities and quality standards. Some specialized in hulls, others in turrets, still others in final assembly. Coordinating this distributed manufacturing network proved extremely difficult. Classification systems became confused. A single mark designation could cover up to 4 actual types of vehicle, and a single type could encompass up to 6 marks. Parts that should have been interchangeable often were not. A component from one manufacturer might require modification to fit a vehicle from another. Total A-27 family production reached approximately 4,016 tanks, including both Cromwells with the Meteor engine and Centaurs with the older Liberty power plant. This was less than what the Chrysler Defense Arsenal alone produced in 5 months of peak output. Exercise Dracula ran from August 4 to September 22, 1943, beginning and ending at Bovington camp in Dorset. It was designed to close when one machine of each type reached 3,000 miles. The tank force included 2 Cromwell Mark IIIs, 3 Cromwell Mark Is, 3 Centaur Mark Is, 3 M4A, 2 Shermans with General Motors diesel engines, and 3 M4A4 Shermans with Chrysler multibank gasoline engines. Firing trials were conducted at Lulworth Ranges. The Centaur, essentially a Cromwell fitted with the older Liberty engine instead of the Meteor, performed worst of all. It covered only 8,492 miles, while accumulating 297 defects and 742 hours of maintenance time, 0.087 hours per mile, nearly triple the Sherman's rate. The best-performing Centaur reached only 2,516 miles when the Cromwells and Shermans hit 3,000. Major General Richardson noted its condition was such as to preclude further running without major fitter attention. The officer reports painted a picture in words that the statistics could not fully convey. Major Ronald of the Westminster Dragoons underwent a complete conversion during the trial. Before the exercise started, he wrote, he was inclined to think that perhaps Sherman was somewhat overrated. He was completely convinced otherwise by the end. The outstanding lesson of this exercise had been the exceptional reliability of the American machines. All his ideas, based on 2.5 years' experience with an armoured regiment equipped with British machines, had to be revised. His operational calculus was devastating. The commander of a unit equipped with Shermans could be confident of taking 99% of his vehicles into battle, at least during the first 2,000 miles of their life. If he were equipped with Cromwells or Centaurs, he would be in a continuous state of anxiety as to whether enough of his tanks would reach the battlefield. Major Ronald noted the extraordinary effort required just to keep British tanks running. Only the very lavish scale of fitters and light aid detachment support had enabled the Cromwells and Centaurs to be brought back to Bovington under their own power. Even then, much night work and long hours had to be worked. The simplicity and reliability of the American machines in contrast with the British production was to him the chief lesson of Dracula. Captain Priestley of the Coldstream Guards documented the human cost in administrative terms that carried real weight. The Cromwells often arrived late at night, involving late meals being required, guides being left out, petrol lorries being kept waiting, and consequent loss of rest and sleep to a large number of personnel. Last parade took at least 1.5 hours, greatly in excess of the time taken by the Shermans. Of the M4A2 Sherman, Priestley wrote that these tanks were no bother from an administrative angle. They often arrived before even the Cromwells. They never required refilling en route. Their last parade was short, and their crews always received their hot evening meal at the correct time. A full night's rest was had by all. Captain Shaw, officer in charge of Sherman records, confirmed that the Shermans on the whole were extremely reliable and gave very little trouble. The only notable Sherman engine issue across all 6 vehicles was on M4A2, number 9, which suffered 2 failed injectors. At the gunnery trials at Lulworth, the contrast was equally stark. Only one tank of British manufacture was able to fire its guns without prior gunfitter attention. Something had gone wrong with sights, with firing mechanisms, with turret traverse systems, on virtually every Cromwell and Centaur tested. All Shermans merely adjusted their sights, drove up, and fired all guns without a hitch. After 2,000 miles of punishing driving, their fire control systems still worked perfectly. The officer in charge of cruiser tank records documented a systemic design flaw that caused recurring injuries. When the vehicle was hot, medical attention was usually necessary for burnt arms, hands, and necks. Brake adjusters on both Cromwell and Centaur required physical contact with scalding hot components. This was not a single incident but an ongoing problem throughout the trial. The same officer noted that the performance of these machines was very disappointing. Without exception, the failures were all old troubles experienced before, troubles that one might have hoped by now ought to have been rectified. Yet he acknowledged that from a purely driving angle, all crews agreed it was a beautiful tank to handle, and the power unit of 600 horsepower was a definite step forward in design. Major General Richardson concluded that the Cromwell was spectacular as regards speed, but doubtful as regards maneuverability and control, owing to unreliability of steering and brakes. It was also doubtful as regards durability over 2,000 miles, owing to the stresses and strains experienced by the Meteor engine when mounted in the hull of a tank and subjected to reverse torque, which an aero engine is not normally called upon to do. He called the Centaur underpowered, unreliable, and unwanted as a tank. A letter dated October 15, 1943 from Alec Richardson, then posted to Washington with the British tank mission, was found in the same archival file. Richardson wrote bluntly that these tanks had made Britain a laughing stock. The Cromwell had had a variety of troubles. He named Waller, a Rolls-Royce representative accompanying the tanks, as most unhappy and wanting them withdrawn as soon as possible. Richardson strongly advised that Britain send out no more tanks until they were reliable. Britain was undoubtedly, he wrote, the world's worst salesman. A second trial was conducted in November 1943 with modifications. This led directly to the Battle Cromwell specification issued by Leyland on February 2, 1944, setting minimum reliability standards for combat deployment. The Cromwell's problems stemmed from a fundamental engineering challenge that its designers had never fully solved. The Rolls-Royce Meteor was a superb engine, but it had been designed to power aircraft, not tanks. Adapting it for ground use required compromises that haunted the Cromwell throughout its early service life. Aircraft engines operate under very specific conditions. They run at relatively constant speeds, optimized for cruise or maximum power. They never reverse direction. They never experience the shock loads of hitting obstacles. They have abundant airflow for cooling. Tank engines face completely different demands. They constantly vary speed and torque as the vehicle accelerates, slows, and maneuvers. They experience reverse torque when the tank brakes or shifts gears. They absorb tremendous shock loads transmitted through the drivetrain. Cooling air is limited by the armour that surrounds the engine compartment. William Arthur Robotham of Rolls-Royce led the team that developed the Meteor at Clan Foundry in Belper. In the autumn of 1940, Robotham and Henry Spurrier of Leyland Motors agreed that British tanks were critically underpowered. The tanks fighting in the Western Desert had engines producing 300 to 400 horsepower. Germany was developing new tanks with 500 to 700 horsepower. Britain needed more power. The solution seemed obvious. Take the Merlin's basic architecture and convert it for ground use. The conversion required significant changes. The supercharger was removed since tanks do not operate at high altitudes. Engine rotation was reversed for compatibility with automotive gearboxes. Aero-type carburetors were replaced with units designed for ground vehicles. Forged aluminum pistons were swapped for cheaper cast ones. The engine was derated to run on low-octane pool petrol instead of the high-octane aviation fuel the Merlin required. Most controversially, early Meteors were assembled from components rejected on quality grounds for the Merlin. Parts that did not meet airworthiness standards but were deemed adequate for ground use found their way into tank engines. Some engines were built from parts recovered from crashed aircraft. This expedient got engines into production faster, but at a cost in reliability. When Robotham's team first tested a Meteor in a Crusader chassis at Aldershot in April 1941, the vehicle reached approximately 50 miles per hour, faster than any British tank had ever travelled. A subsequent 3,600-mile endurance test revealed deeper problems. The suspension and transmission could not withstand twice the power they were designed for. Components failed. Bearings wore. Olkovsky, a Soviet trade representative who visited Chobham proving grounds on November 13, 1942, observed early Cromwell problems firsthand. The tanks showed smooth driving on cross-country terrain, he reported. However, they were plagued by minor defects in the gearbox. After 5 kilometers off-road, the water in the radiator started boiling. Suspension springs broke several times. The Christie suspension, chosen for its speed capability, introduced its own maintenance burden. The Cromwell was prone to throwing tracks at high speeds or during sharp turns. Engine revolutions per minute had to be limited by a governor, and top speed was formally reduced from over 40 miles per hour to 32 miles per hour to preserve suspension components. Damaged Christie components required removing tracks, wheels, and outer armor plate to access, a significant field maintenance handicap. Work that could be accomplished in hours on a Sherman might take days on a Cromwell. The Sherman, by contrast, was designed from the start for ease of maintenance. Every component was designed for accessibility. The Sherman's own engine situation was more complicated than often portrayed. Rather than wait for a single ideal power plant, United States Army Ordnance deliberately pursued 4 different engines simultaneously to prevent production bottlenecks. Each told a different story about American wartime manufacturing. The Continental R975 Radial was the original Sherman engine, a 9-cylinder air-cooled aircraft derivative producing 350 to 400 horsepower. It was actually the least reliable of the 4 American options. British experience with this engine in North Africa showed engine life of only 700 to 900 miles, or 180 to 200 hours, requiring inspection after every 100 hours. The Ford GAA-V8 was the standout performer. Originally designed as a V12 aircraft engine, Ford cut it to 8 cylinders, producing 450 to 500 horsepower from 18 litres of all-aluminum dual overhead cam construction. In the critical 1943 to 1944 comparative trials, M4A3s with Ford engines dramatically outpaced every other variant. One covered 2,097 miles in 203 hours, while the R975-powered M4 failed after just 15 hours. The United States Army kept the M4A3 largely for its own forces, rarely supplying it through Lend-Lease. The General Motors 6046 twin diesel consisted of 2 GM6 71-2 inline sixes coupled together. It achieved the highest average speeds in trials and was rated very high for reliability. Its diesel fuel reduced fire risk, and the twin-engine configuration allowed crews to disengage one engine and limp away on the other. The Chrysler A57 multibank was the most audacious solution. 5 Chrysler flathead inline-6 automobile engines bolted together in a star pattern, creating a 30-cylinder power plant producing approximately 425 horsepower. Early examples proved troublesome, but after Chrysler fitted improved exhaust valves and chrome-plated piston rings, the A57 transformed. British data ultimately rated the M4A4 with the Chrysler engine as one of the most reliable Sherman variants. Soviet evaluators who tested the Cromwell at Kubinka proving grounds in 1944 reached conclusions that echoed Exercise Dracula. 6 Cromwell 4s built in May of that year arrived at Baku on August 18, 1944 via the southern Lend-Lease route through Iran. They reached Kubinka in early September. 3 tanks were identified by serial number in the Soviet records. Tank T-187888 was used for initial trials from September 8 through 11th. Tank T-187887 survived and is now on display at Patriot Park. Tank T-187866 was partially disassembled and used as a target in winter 1945. Full mobility trials in late October produced specific data. On asphalt, the Cromwell achieved an average speed of 44.7 km per hour, with fuel consumption of 225 litres per 100 kilometers. On dirt roads, average speed dropped to 22.7 km per hour, with consumption rising to 353 litres. Off-road, average speed was 24.3 km per hour, with consumption reaching 370 litres per 100 kilometers. The devastating comparison was fuel consumption. The Cromwell required 280 litres per 100 kilometers compared to just 180 for the M4A2 Sherman and 170 for the Soviet T-34. Soviet testers were scathing about construction. It seemed that the tank's designers knew nothing of the T-34 and its sloped armour plates, they wrote. The evaluators had nothing good to say about the Cromwell's hull and turret due to the riveted frame construction with massive protruding rivets. The turret was very cramped compared to both Soviet and American designs. The tank did not behave as confidently as an M4A2 Sherman or a T-34 in difficult terrain. Its narrow tracks gave poor flotation in mud. Its high ground pressure caused it to sink where wider-tracked vehicles passed easily. The final verdict was unambiguous. The Cromwell 4 tank could not be recommended for import. The evaluators concluded that yes, the Cromwell 4 was the best tank made in Great Britain at the time. The problem was that it was inferior to the Sherman in all respects except speed. By D-Day in June 1944, the Battle Cromwell specification had addressed the worst mechanical defects. The 7th Armoured Division, the famous desert rats who had fought from El Alamein to Tunis, fielded Cromwells in their armoured regiments. They landed on Gold Beach on June 7th and moved inland to begin the liberation of France. Bill Bellamy served as a troop leader in the 8th King's Royal Irish Hussars, the reconnaissance regiment of the 7th Armoured Division. He landed on D+3 and was present at the Battle of Villers-Bocage on June 13, 1944. His wartime diaries, kept against regulations, later became the memoir Troop Leader, considered one of the finest British tank crew accounts of the war. Villers-Bocage exposed the Cromwell's combat limitations beyond reliability. Captain Pat Dias, adjutant of the 4th County of London Yeomanry, stalked the Tiger of SS Obersturmführer Michael Whitman from behind with his Cromwell. But the Cromwell's shells had no effect on the Tiger's heavy armour. Whitman destroyed Dias's tank. The Cromwell's reverse speed was painfully slow, a critical weakness when trying to escape Tigers in narrow streets. After the Normandy breakout, the Cromwell proved its worth in the exploitation phase. The 7th Armoured Division advanced rapidly during the pursuit across France, demonstrating the speed and mechanical endurance that had been its design purpose. The Meteor engine in its final Battle Cromwell form proved more reliable during this phase. But other vulnerabilities remained. A 1946 Royal Army Medical School report found that the Cromwell's low ground clearance and thin floor plates made it substantially more at risk from damage by a mine blast than the M4 Sherman. No. 2 Operational Research Section of 21st Army Group produced reports on tank casualties during the exploitation phase after crossing the Seine. They found not many losses due to enemy action, but a significant number of mechanical failures, analysed by formation. Lieutenant General Sir Giffard Martel, former commander of the Royal Armoured Corps, wrote in his 1945 book, Our Armoured Forces, that the Sherman tank was a reliable machine. The Tank Museum describes this assessment as rather arrogant, noting that Martel failed to recognise the flexibility that American tanks gave British forces and the adaptability that allowed rapid field modifications. Colonel Dmitry Loza commanded M4A2 Shermans in the Soviet Red Army from Ukraine to Manchuria. He had 3 tanks destroyed under him during the war and earned the title Hero of the Soviet Union for his actions. His memoir, Commanding the Red Army's Sherman Tanks, provides a unique perspective on the Sherman's reliability from a non-American user. Loza praised the Sherman's durability during extended road marches. Soviet doctrine emphasized deep penetration operations where tanks might drive hundreds of miles before engaging the enemy. A tank that broke down on the approach march was worse than useless. The Sherman started in the bitter Russian cold. It ran through the summer dust. It climbed the Carpathian passes. Loza noted a feature the T-34 lacked. An auxiliary power unit kept batteries charged without running the main engine. Soviet tankers on the T-34 had to run their diesel engines periodically just to charge batteries. Sherman crews could run their radios and heaters while the main engine sat cold. After Germany's defeat in May 1945, Loza's unit redeployed to the Far East for the invasion of Manchuria. They crossed difficult terrain in August 1945, a testament to the Sherman's endurance in extreme conditions. Reliability proved most decisive during exploitation and pursuit phases when advancing forces outran their logistics. After Operation Cobra broke German lines on July 25, 1944, General George Patton's Third Army raced across France with Shermans driven hundreds of miles on their own tracks without systematic breakdown. The fuel ran out before the tanks broke down. German heavy tanks could not match this mobility even when fuel was available. The Tiger's complex interleaved road wheels were maintenance nightmares. The Panther's final drive failed with depressing regularity. German tank recovery vehicles were constantly busy while American units pressed forward. The M4A3E2 assault Sherman, known as Cobra King, led the column that relieved Bastogne during the Battle of the Bulge on December 26, 1944. This heavily armoured jumbo variant with its 75mm gun belonged to Company C, 37th Tank Battalion, 4th Armoured Division, commanded by Lieutenant Colonel Creighton W. Abrams, Jr., who would later become Army Chief of Staff and give his name to the M1 Abrams tank. The full crew of Cobra King that day has been documented by historians. First Lieutenant Charles Perry Boggess, Jr. commanded the tank. Born January 7, 1912 in Catlin, Illinois, he had been a pre-war undertaker before entering service on March 10, 1942. Private Hubert S. Smith drove. Private Harold Hafner manned the bow gun. Corporal Milton Dickerman served as gunner. Private James G. Murphy loaded ammunition. 3 days earlier, on December 23rd, Lieutenant Charles Trover had been killed by a sniper while standing in Cobra King's turret. Boggess replaced him. The Sherman's reliability underpinned the entire relief operation. Between December 19th and 20th, the 4th Armoured Division executed a 161-mile road march in 15 to 19 hours, under total blackout conditions, pivoting from its advance toward Germany to reach the Bastogne area. Brigadier General Albin F. Irzik, commander of the 8th Tank Battalion, recalled that remarkably, they had travelled 161 miles over roads that were sometimes bad, without maps and without confusion. That the division's Shermans completed this march without mass breakdowns, after 5 months of continuous combat, was itself a powerful reliability testament. On December 26th, Company C attacked with just 9 tanks at approximately 15 hours, supported by 2,340 artillery shells. Boggess later told the European Stars and Stripes that the Germans had 2 little towns of Cloquimont and Assenois on the secondary road they were using to get to Bastogne. They were going through fast, all guns firing, straight up that road to bust through before the Germans had time to get set. Corporal Milton Dickerman, the gunner, added that he used the 75mm like it was a machine gun. Murphy was plenty busy throwing in shells. They shot 21 rounds in a few minutes, and he did not know how much machine gun ammunition. Contact was made at approximately 1650 hours when Lieutenant Dwayne J. Webster of the 326th Airborne Engineers, 101st Airborne Division, approached the tank. He said that he was Lieutenant Dwayne J. Webster and that they were mighty glad to see the relief force. Cobra King itself had been knocked out of action in November 1944, repaired, and returned to service. This was direct demonstration of Sherman maintainability. Company C was reduced to just 4 operational tanks after the breakthrough. Boggess later reflected that he believed it was appointed to each man to have a few minutes of glory in his life. The Sherman's field adaptability was equally decisive. Sergeant Curtis G. Culin of the 102nd Cavalry Reconnaissance Squadron invented the Rhino hedgerow cutter. Faced with the thick Norman hedgerows that stopped tanks cold, Cullen welded steel teeth cut from German beach obstacles onto a Sherman's bow. The tank could now cut through hedgerows rather than climbing over them and exposing its thin belly armor. By the eve of Operation Cobra, 60% of 1st Army tanks had been fitted with these cutters. The modification was simple enough that unit mechanics could accomplish it with available tools. In the Pacific, Marines demonstrated the Sherman's durability under the most extreme conditions. The 5th Tank Battalion Special Action Report for the Iwo Jima operation, commanded by Lieutenant Colonel William R. Collins, contains a verified assessment. The all-around performance of the M4A3 tank was exceptionally good. Approximately 150 Sherman tanks deployed across the 3rd, 4th and 5th Tank Battalions at Iwo Jima, the largest Marine tank force of the Second World War. The M4A3 made its combat debut on the island. On D+1, February 20, 1945, the 5th Tank Battalion had 31 of 50 tanks operational after a day of fighting across volcanic terrain that bogged tanks, through tracks, and exposed them to mines and satchel charges. At Peleliu in September 1944, the 1st Tank Battalion of the 1st Marine Division demonstrated extraordinary Sherman recoverability. 45 of 46 tanks were knocked out at some point during the battle, but only 9 were permanently lost. This was an 80% recovery and return to service rate. On Bougainville, the 754th Tank Battalion reported that the M4 medium tank was almost ideal for jungle warfare. It had the power to crush and penetrate undergrowth. Its size and heavy armor rendered it almost invulnerable to Japanese anti-tank weapons. No M4 tanks were even damaged by the enemy at Torokina. Corporal Leighton Wilhite served as driver of M4A3 Lucky in 3rd Platoon, C Company, 5th Tank Battalion at Iwo Jima. He was 19 years old. On March 1, 1945, at Hill 362A, he earned the Bronze Star with valor for assisting in the rescue of the crew of the tank Genie under enemy fire. His oral history is preserved at the National Museum of the Pacific War. Major Robert M. Neiman earned the Navy Cross serving with the 4th Tank Battalion. He fought at Roy Namur, Saipan, Tinian, and Iwo Jima. At Saipan, he had to switch tanks twice under fire after mines disabled them. His account appears in the book Tanks on the Beaches. At the Battle of the Bulge in December 1944, the harsh Ardennes winter exposed mechanical limits on both sides. Temperatures dropped severely. Tanks froze to the ground overnight and had to be freed. Engine oil congealed. Batteries went dead. Yet the Sherman's standardized parts and echelon repair system kept units fighting. When a tank broke down, parts were available. Mechanics knew exactly what to do. A damaged Sherman could often be returned to service in hours. German Panthers and Tigers, superior in armor and firepower, sat immobilized by fuel shortages and mechanical failures. Their complex systems demanded specialized maintenance that was simply unavailable in the frozen forests. Stephen Zaloga, one of the foremost historians of armored warfare, assessed in his book Armored Thunderbolt that the Ardennes was the Sherman's shining moment of the war. Reliability translated directly into operational mobility. The 2nd Armored Division's 90-mile overnight road march during the Bulge was only possible because Shermans kept running. The reliability gap carried a human cost that official statistics could not capture. Every breakdown was a crew exposed to enemy fire while waiting for recovery. Every hour spent on repairs was an hour not spent training or resting. Every tank that failed to reach the battlefield was firepower that could not support the infantry. British armoured divisions were equipped en masse with American Shermans from 1943 onward, accepting the practical necessity that British industry could not meet their needs. The Sherman, though itself outclassed by German heavy armour, was at least reliable, adaptable, and available in large numbers. The Ministry of Aircraft Production refused to release Meteor engines until its own Merlin demands were met, forcing the Centaur stopgap with the unreliable Liberty engine. British aviation took priority over British armour. Rover and Morris eventually established Meteor production lines, but required American machine tools imported under Lend-Lease. British tanks depended on American industrial equipment to be built at all. Despite its troubled early service, the Meteor engine proved its fundamental soundness in the years that followed. The engine that caused so many difficulties in the early Cromwell would power the Comet tank that arrived too late to see significant combat before Germany's surrender. It would power the Centurion, widely considered the first truly successful main battle tank, which served with distinction from Korea through decades of Cold War service. Duncan Sandys, British Minister of Supply, said in 1963 that he regarded the adoption of the Meteor tank engine as the absolute turning point in the history of British tank development. He was right. The Meteor became one of the most successful tank engines ever built. The problem was never the Meteor itself. It was the rushed wartime timeline that put an immature powertrain into combat before its development was complete. The Cromwell served on after the war, equipping British armoured units in the occupation of Germany. Approximately 3,066 Cromwells were built, plus another 950 Centaurs. A total of 4,016 vehicles in the A27 family. The Sherman family exceeded 49,000 vehicles. The numbers told their own story. Today, preserved examples of both tanks can be found in museums around the world. The Tank Museum at Bovington in England maintains running examples of the Cromwell and multiple Sherman variants. Visitors can hear the distinctive sound of the Meteor engine, still powerful after 8 decades, and the steady rumble of the Continental Radial that carried American tankers across Europe and the Pacific. The story of the Sherman and the Cromwell is not simply a tale of good engineering versus bad. British engineers were not inferior to their American counterparts. The men who designed the Merlin engine and adapted it into the Meteor were among the finest automotive engineers in the world. The problem was systemic, not individual. Two nations approached the same challenge with fundamentally different industrial philosophies. One approach produced machines that pushed the boundaries of performance. The other produced enough machines to win. America's automotive industry had spent decades perfecting interchangeable parts mass production. When Detroit turned to tanks, those methods came with them. Standardized drawings that any factory could follow. Cross-factory parts compatibility that any mechanic could rely on. Assembly line quality control that caught defects before they reached the battlefield. Britain's engineering tradition emphasized craft, performance, and individual excellence. These qualities produced the Merlin engine that won the Battle of Britain. They produced magnificent aircraft. They struggled to produce thousands of reliable tanks. The Sherman won the reliability war not because American engineers were smarter, but because American factories were different. Every Sherman that rolled off an assembly line in Detroit or Los Angeles or Cleveland was built to be identical to every other Sherman. Every Cromwell that emerged from Birmingham or Coventry carried the work of craftsmen who had fitted its components by hand. In peacetime, the British approach produced magnificent machines. In total war, the American approach produced enough machines to bury the enemy in steel. The men who crewed these tanks deserve recognition. They fought in vehicles that were never fully adequate to their task. Neither the Sherman nor the Cromwell could meet a Panther or Tiger on equal terms. Both were vulnerable to German 88mm guns. Their crews knew this and fought anyway. What the Sherman gave its crews was confidence that their tank would start in the morning, confidence that they would reach the battlefield, confidence that if something broke, it could be fixed. The Cromwell gave its crews speed and agility but also uncertainty. Would this be the day the engine failed? Would the track throw during a sharp turn? Would the steering hold on that downhill slope? In the end, the Sherman's greatest weapon was not its gun or its armor. Its greatest weapon was reliability, the ability to be there when needed, mile after mile, battle after battle, from the sands of El Alamein to the frozen forests of the Ardennes to the volcanic ash of Iwo Jima. The Cromwell was faster. The Sherman was there. That made all the difference.